All right, the recorder is on. And if you are thinking, whether, we have a recording for the material that we talked about during the power fail, it is from yesterday's class. So the Monday, Wednesday class, went through basically the same content, and that was recorded and uploaded to YouTube already. So if you want to get a YouTube recording of the material that we talked about on Tuesday when we had a power fail, it is now available from the Monday, Wednesday class. Yeah, it's already up on YouTube. So if you are to go to YouTube, my channel, and then go to videos, the lecture from yesterday, which is CISP 310 from yesterday, that covered the same material that we covered the other day when we had a power fail. All right. So with that said, I am going to continue with what we'll be talking about today. So I think I have decided not to push the lab thing yet. Okay, so we are gonna stay, kind of on the same uh, track, as before. All right. So now that we are done with addition, we are moving on to subtraction. Okay, and it's gonna be the same template as what we did on Tuesday. So we'll start with base 10 subtraction, and then we're going to move on to the generalization. So that's kind of what I usually do is, just, use examples and then, talk about the generalizations. So just like last time, we're going to start with a subtraction example. And I'm going to start with something like this, 213, and we are subtracting from it. Now, this time I'm going to switch to the long format right away. Well, actually, I take it back. I'm going to use the usual format, and then we'll switch to the long format after this. So let's say we have 115 in this case, and we want to perform this particular subtraction. So the way we do it is we look at the 3, we look at the 5. 3 minus 5 is, oh, 5 is greater than 3, so we cannot easily, represent, what the difference is. So this is when we have the concept of borrowing, which is the counterpart of carrying, because 3 is less than 5. So the only way for, people to make sense of the subtraction is to say, well, the next column, which is digit 1, can I borrow 10 from you? So now instead of 3, we have 13. 13 minus 5 is a 8. Okay, there we go. And then we just, put a little mark here to say that, yeah, we borrow from that column. So now when we work on the digit 1, we have 1 minus 1, which is 0. 0 minus 1. Darn it, we have to borrow again. So this time we have to borrow from digit 2. So every time a borrow is from the next column is quote unquote a quantity of 10. So that means I just borrow 10. So now I have 10 minus 1, and the result is 9. So now we have 2 minus 1, which is 1, and then 1 minus this one here is a 0. So now we know the answer to that question, which is what is the difference between 213 and 115, is just 98. So that's how I remember how multi-digit is supposed to work, or multi-digit subtraction is supposed to work. The notation part, I think, the little one, may not be here for some people. It may be up, down, somewhere else. I don't really know. But, this is the general way to do it. So do we have any questions about the general idea of multi-digit subtraction in base 10? So we feel comfortable enough with this? Okay, all right. So now we're going to do exactly the same thing that we did the other day with addition, which is let's do this in a very kind of awkward and tedious format, but everything is going to be spelled out in this case. So now we go like, okay, same thing, 213 minus 115. But this time I have one more row here and then one more row down here. And then the default borrow is a 0 because there are no digits to the right hand side of digit 0 in this case. So we put a 0 here. And now we go like, okay, what is the single digit difference? Not sum this time. What is the single digit difference between 3 and 5? In other words, if I subtract 5 from 3, what is the single digit difference? It'll be 8. It's 8 because with a borrow, it is 8. So this one is 8 with a, but because of the borrow. And then we have 1 minus 1, the single digit difference between 1 and 1. That's an easy one. And then the single digit difference between 2 and 1 is just 1. Okay. Now we have to figure out the borrow here. 3 minus 5 needs a borrow, so that's a 1 already. 8 minus 0 does not have a borrow, so we can put the 8 here. And now we move on to digit 1. 0 minus 1 is, okay, we need a borrow here. So now we have 10 minus 1, which is a 9. And now finally we have 1 minus 1, which is a 0. And also on top, 2 minus 1 does not need a borrow. 1 minus 1 also does not need a borrow. So we have an overall borrow of 0. So I'm going to pause a little bit here and see if we are comfortable with what we see on the right hand side, which is the kind of long and tedious way to spell out what we normally write in a much simpler way on the left hand side. So are we doing okay with the longer and more tedious format? Okay, I see nods. Okay, but if there are any questions, now would be a good time to ask. Okay. So now, okay, I'm not seeing any questions. So now I'm going to name these rows. We have X, Y, Q, but this time we have T, and then we have D for difference. So the last two rows are named differently because this time we're dealing with subtraction, okay? And T is quote unquote taking away something, which is borrowing, and then D is difference. So, but you don't even have to remember why I chose those particular letters. It's just the a designation for a particular row. Okay, so that's that. So now I want to know how I can compute borrowing. So I use about the same thing. Okay, U and V are single digit in base 10. I want to know whether subtracting V from U will end up with a borrow of 1 or a borrow of 0. So this is analogous, or this is the counterpart to the C function in adding. It is a borrow function. It determines what is the borrow when we subtract V from U. So now the question is, okay, let's go through a few examples to see how it's supposed to work. So B of 5, 6 is a 1 because when you subtract 6 from 5, you need to borrow. B of 2, 6 is a 1. B of 0, 0 is a 0. B of 5, 0 or 5, 2, say, is a 0, and so on. So are we understanding what the borrow function is supposed to do? It will give you either a 1 or a 0. And the determination, if you look at this pattern here, seems pretty simple, right? So how would we write the borrow function? In other words, how would we define the borrow function in this case? It looks like when v is greater than u, then we have a 1 as the return value. Otherwise, we have a 0 as a return value. Is that observation consistent with your thinking? Yep, go ahead. And we're going to use a ternary operator. So do you want to give it a try? Yeah, okay. Just colon, not semicolon. Yep. Sorry for nitpicking, but that's my job. All right, that is correct. Okay, it is a ternary expression. Normally, I would do it in just the opposite way. This is correct, okay? It's just for consistency with my notes. I usually reverse these two so that it would just say that if u is less than v, then we have a result of 1. Otherwise, we have a result of 0. Is that okay? All right, cool. All right, nice. So can everybody kind of see that, oh, this is kind of like a carry function, except like a C function, except this one is applicable for subtraction. But it works kind of the same way, except it is in the opposite direction. Are we good so far? All right. And then we are going to erase this portion here. All right. And then we'll go ahead and do the R function. So the R function is also just doing the single digit thing, but this time it is a single digit difference for a subtraction. So we'll go like, okay, what is R of 2, 6? What do you think it is? If we are to subtract 6 from 2, what is the single digit difference? No. So taking into consideration that we can borrow, what is what is the difference between 2 and 6? What is the It's 6, okay? Because if we have a borrow, then we have 12. 12 minus 6 is 6. Okay, there we go. Let's try your 5 and 7. Okay, what would that be? That'll be 8. What is 7, 5? It's 2, just regular 2, because 7 minus 5 is really just 2. And then we'll have one more, 0, 3. What would that be? It'll be a 7. Very good. All right. So by using these examples, we kind of know by observation, we kind of see, oh, okay, so this is what it's supposed to return. But how do we generalize from the examples to the actual definition? In other words, what should I put here as the quote unquote definition of the single digit difference of u minus v? That would be the purpose of this R function. Go ahead. Okay, we could do that. Okay, so yep, okay, that's good. So we have 10 plus u and then minus v. Otherwise, yep, that works. Very good. All right. So that's one way to do it. There's another way to do it, which is a little bit on the cheating side. It it looks simpler, but it's actually more complicated. So I'll give you get if you I'll give you that answer too. You just blindly add u first, but then you just mod this whole thing with 10 afterwards. So it looks simpler, but it is actually a lot more difficult to compute because of the mod, which is a division. So both are okay. They both work. Okay. All right. So now that we have the b and the r function, now we want to establish, the relationship between the digits. So this is where things really get more abstract because this is where you go like, oh, okay, so we are really trying to figure out how do we come up with this 0 here? How do we come up with this 1 over here? How do we come up with this 8 over here? So that is something that we also did with addition, except this time we're applying the same kind of reasoning to subtraction. Okay, so we'll start with q. So not even designating which digit, I just call it digit I. What is q of I? You can make use of x, y, q, t, d. You can also make use of the b function as well as the r function as defined on the whiteboard at this point. So what would that look like? What is q of I? Go ahead. R of, well, u and v are only here to define the function, but it's not really a part of the rows. Okay, x, I, y, I. So now you have to be more careful because subtraction is not commutative. Wait, Tech, you just use a word that I may not remember. What is commutative in algebra? Yes, go ahead. Yes, so you can switch the left-hand side and the right-hand side, and it does not change the outcome of the operator. So addition and multiplication are commutative, subtraction and division are not commutative. Okay, so that means in addition, we could have easily switched between the u and the v. The ordering does not really matter. But in subtraction, you really have to use it in this particular order. Are we doing okay so far? All right, so that's Q. Let's work with the next one that is also easy. What is d of I? So in this case, d is designating the difference row. It is not just a digit, it is the digits that belong to the difference. So what is d of I? If you look at the addition structure, it actually has a lot of resemblance. So what do you think? R of QI DI. Yep. TI. Yep. So let me switch back. There you go. TI. That is correct. Very good. So what about T? So T, just like K, is dependent on the previous column. So now we can only say something about T of I plus 1 because we want to refer back to the column I in this case. So if you remember K of I plus 1, this one has exactly the same structure, but using a different function so that we, instead of computing the carries, we're now computing the borrows. So what do you think it's going to look like? So I'm gonna take a pause here because I know some of you already know the answer and some of you may not know the answer. So you don't have to tell me whether you know the answer or not, or you know how to derive the answer. But for people who cannot remember, what k of I plus 1 or how it is defined in addition from the lecture on Tuesday, what do you think I have to say? And that question is open to the whole class. Okay, so what do you mean by studying more? I'm not nitpicking. I'm just asking, can you elaborate? Yep, yep. And we can now see why it is important because I reference back to things that I have already mentioned, making the assumption that people understand and remember those things. Now, if you say, okay, I actually get it, but I have to refer back to my notes to read about it, that's actually okay. It's not a problem as long as you know where to find it. Okay? Because that means you already understand the concept, but you might need a little bit of help just to kind of spell out the whole thing. Okay? Because I'm not expecting you guys to memorize all of these things and know it by heart. Okay? But if you say, I know what this is, I know where to find it, and that'll be good. Okay? So why do you think I mentioned these quote unquote expectations? Is it me being, you know, the father and want to enforce things in this class? Or do you think there is actually practical reasons that I'm trying to mention this to get people to do it? For people who do not keep up with the content, it will be very difficult. So it is important to keep up with the material. And then the second thing that is really important is I only have so much time in this class to teach all the concepts that I think I need to teach. So that means I cannot spend a lot of time to go back and forth. It's like, okay, remember this is what we talked about, and then spend another 2 or 3 minutes to talk about it. It is important to oh, it's important to have everybody in this class to take on that responsibility to keep track of all the material so that when I try to use something that I have mentioned from a previous class, you guys go like, okay, I know what it is, or at least I know where to find it. Okay, so those are practical reasons why I have to make statements about this kind of stuff. Okay, I'm not trying to point fingers to anyone. I'm just trying to make sure that you all have what it takes to be successful in this class, which is actually for selfish reasons, because if you guys are not successful in this class, it reflects on my numbers when I get my performance review. So, yes, it is all for selfish reasons, which accidentally help you too. It's always good to get all of this out in the air. Okay, so what about t of I plus 1? Because it has the same structure as k of I plus 1. The only thing we have to change is instead of c, we have b. That's it. Okay, so this is the borrow of xi minus yi plus the borrow of qi minus ti. That's it. Okay, so structurally speaking, this is how subtraction works. But what we want to focus on is not so much this part here, because this part is subtraction specific. But if you are to focus only on this part here, which is the structure of who depends on whom and how it works out, you go like, oh, the only change from what we have learned already is we don't use K, we use T over here, and then we don't use C, and instead we use B over here. That's it. Okay, that is the pattern. Okay, so with this, let me ask you also, if I want to change this, method of performing multi-digit subtraction in base 10, and I want to go like, what about base 7? Can we do this in base 7? What would be your answer? Okay, I see nods. How do we do it? Which part do we have to change? Everything that mentions 10 needs to now say 7. That's it. So let me identify the tens over here, this or this, depending on which definition you want to use. Oh, that's one more here. And when you look at the b function, it does not even mention the base. It doesn't need to know what base you're in, because as long as the single digit u is less than the single digit v, we need to borrow. Are we good so far? Okay. So in your notes, you might want to write this down, because I don't need to remember these things because I already know this. So you might want to write this down before I switch to the next slide, which is going to use a base 7 example. So are we ready to go? Okay, all right. So now we move on and go like, okay, let's do some base 7 subtraction. So we'll do a 213 again, but this time it's not 213, it is 213 in base 7. And what was the other number that I used? 115. Yeah, that actually works too. So, but this time it is all in base 7. So let me emphasize this is all in base 7. All right. So we got X, we got Y, we got Q, we got T, and then we got D. All right. And this is a 0 because it is the borrow from a digit on the right hand side, and this is the rightmost digit to begin with. So there's nothing that will borrow from the column corresponding to digit 0. Okay, so now we go like, okay, what is the single digit difference between 3 and 5, or 3 minus 5? You go like, uh, 8. Nope, it's not 8, because you cannot even have a digit 8 in base 7. In base 7, you only have the digits from 0 to 6. Okay, so that doesn't work. So what do? Reference back to the definition. Okay, always go back to the definition. In this case, it is the R of xiyi. Okay, so it's the R of 3, 5. How does that work? Well, if 3 is less than 5, then we add the base, which is 7, to the 3 first, which will give us a value of 10. 10 minus 5 is a 2. Hmm? 10 minus 5 is a 5. Thank you. My arithmetic is questionable. That's why we have calculators. All right, it is a 5. Thank you. But we also have a borrow here. We have a borrow here because 3 is less than 5, so we have a borrow here. Do we have a borrow of 2? No, because 5 is not less than 0. And that's why, we have basically 1 plus 0, which is a 1 over here. Is that okay? All right. So now we move on to, well, okay, let's do this part too. So we have 1 minus 1, regardless of the base, 1 minus 1 always has a partial difference, a single digit difference of a 0. So that part is easy. But 0 minus 1 is like 9. Nope, because this is not base 10. So in base 7, it would be it would be 6. Yep. So 1 minus in 1 minus 1 we don't need a borrow, but in 0 minus 1 we do need a borrow. So from the perspective of the b function, this will give us a 0, this will give us a 1. 0 plus 1 is a 1, so we put that one over here. 2 minus 1 is 1, 1 minus 1 is a 0. And then we look at 2 minus 1 does not need to borrow, so the borrow is a 0. 1 minus 1 does not need to borrow, so the borrow is going to be 0. 0 plus 0 is going to be a 0 over here. Do we have any questions about this particular process? Yep. So we'll figure that out. We'll try to figure out, is it possible to have a borrow of 2 from a digit to the right-hand side? So we'll do the same kind of analysis like what we did with addition, and then we'll see, whether that works out or not. Okay. All right. So now we look at this and go like, yeah, but Tack, you can say anything you want. We don't really know whether it's supposed to work or not. So we're going to do the same thing as what we did with addition, which is converting these base 7 numbers into a decimal number. So this is 2 times 49 plus 1 times 7 plus 3 times 1. So that would be 98 plus 7 plus 3, which is 108 in base 10. So once again, I'm doing this because I'm practicing base conversion, and I'm also using this as an opportunity to double check to see if the process of multi-digit subtraction is working or not. Okay, which is the same thing that I did on Tuesday, but for addition. So now we look at 105 also in base, oh, not that, 115. So let me fix that. Okay, 115 in base 7 is 1 times 49. Where is that 49 coming from? It's 7 squared, because this one here is digit 2, which means this 1 is telling me in terms of quantity, we have 1 of 7, which is my base, to the power of 2, which is the position of the digit. Okay, so now we also have 1 of 7, and then we also have 5 of 1. So that'll be 49 plus 7 plus 5. So that's going to be 56 plus 5, which is 61. Yep, that looks good. All right. So now we go all the way. So now we perform the subtraction in base 10. So 108 minus 61 in base 10. I'll do this, the quick way to do it. So 7, and this is going to be a 4. So it's 47 in base 10. So now I want to convert 47 in base 10 back into base 7 to see if I'm getting back 0.65 in base 7. So when you do this, you go like, okay, so what are the powers of 7? 7 squared is 49, 7 to the power of 1 is 7, 7 to the power of 0 is 1. So now you look at 47, it does not have any 49s because, set 47 is less than 49. It has 6 sevens that will account for 42. And once we have 42, then we have 5 as a remainder. So that means, in base 7, the quantity that we know as 47 in base 10 is going to spell as 065 in base 7, which is exactly what we got. So I just double checked my own work to make sure that the subtraction part is done correctly. But I did that by base conversion and then do the base 10 subtraction and then base conversion back. So I'm doing two base conversions. Um, Twice I did it from base 7 to base 10, and then once from base 10 back to base 7. So from this perspective, I just gave myself some exercises. Okay, so even though the reading material did not mention anything about let's practice this, okay, I in my own verification of the entire calculation, I just gave myself some opportunities to exercise what I have learned. Okay, I don't know exactly how to teach this, okay? But if you can spot these opportunities when you're reading some material, it's like, okay, according to this, I should be able to get this. And then if you can figure out how to verify the answer, only using the content and the material that you have learned already, it is a I would call this a really effective way to study because you are exercising things that you have been learning all along and making the connections between all those concepts at the same time. So I would say it's a very effective way to study, but I cannot teach you quote unquote the technique because it has to do with pattern recognition. You have to recognize, oh, I can do this, okay? And I cannot teach you how that recognition part works. Is that okay? All right. Um, yeah, I was very tempted to talk about MBTI, the personality type thing, because according to that, okay, your the four letters, when you do the personality test, there are certain types of people who just intrinsically can do pattern recognition better than others. Okay, but I don't want to go too much into that because, as I said a little bit earlier, we don't have all the time in the world to do it. All right, so we are moving on to base 2. Okay, just like in binary addition, we are now working with binary subtraction, which means U and V as single digits can only be zeros and ones. So now U can be 0, 0, 1, 1. While U is 0, V can be 0 or 1. While U is 1, V can also be 0 or 1. In other words, the truth table looks pretty much the same, okay, from the setup perspective as the other one in addition, except this time we have the B function and the R function. So we're going to work with the more difficult one first. So let's work with the B function. So with the B function, we are saying, okay, there's no borrow in this case. There is a borrow of 1 in this case. No borrow here, and then no borrow here. Okay, and it's already looking kind of icky because it doesn't match any binary or Boolean operator that we know. Okay, well we'll deal with that later. So now we move on to the R function. The R function in this case is the single digit difference between when we perform U minus V. So when U minus 0 minus 0 just has a single digit difference of 0, 0 minus 1 is the only one that's tricky. Okay, so in base 2, we add the 2 to the 0 first, and then we perform the subtraction of 1, which means we end up with 1. That is correct. 1 minus 0 is always a 1 regardless of the base. And then the last one is 1 minus 1, which is always 0 regardless of the base. All right. So at this point, if you recognize this and go like, Dak, that R function is the same as for addition, then I would say, congratulations. Okay. You understand the R function for addition, and not only that, you are now recognizing that the R function for subtraction in base 2, but only in base 2, is identical to the one for addition. All right. So that's cool. That is really cool. All right, but the B function is a little bit of a nasty one. So with the R function, we can go like, oh, okay, so we can just say that this is U exclusive OR with V. Okay, that's the mathematical symbol. You can also just spell it out. Or for those of you who go like, okay, I just really want the basic Boolean operators, fine, we'll just kind of do the same thing as last time, which is this thing here. Okay, yes, question? Yes, but we want to convert everything to Boolean operators. So now we go like this, okay? So let's figure out how to use only Boolean operators. The nice thing is only one row of the entire table needs to be a one, and that happens only when U is false and U and V is true. So that means, oh, okay, so if I invert the U so that when it is false but the expression is true, and then do a conjunction with V itself, that will give me the answer because the expression that I just wrote, which is the negation of U, the whole thing, logical AND with V, this expression is true only for the second row of the truth table. I have just made a claim. What are you going to do about it? Check it, right? So you go like, okay, fine, let's check this. When V is a zero, because V is over here and it's in a conjunction, so that means the whole conjunction has to be false. That explains this zero and also this zero. Okay. What if U is um, what happens when V is a one? Then it depends on U because you have one side of the conjunction being true. So now whether the whole conjunction is true or not depends on the other side. So on this row, because U is false, not U is true, so you end up with true and true. So that's why we have this one here. For this row, because U is true to begin with, not true is false. So you have a false on the one side of the conjunction, and that's why we end up with a zero here. So it all checks out. Okay. So when you're studying, you have to kind of use this mindset. Okay. Here's a claim, and how do I know the claim is correct? Okay. Use what you have learned already, or try to use what you have learned already to do your own verification. It sounds like you're reinventing the wheel. If the professor told me something, I don't have to derive it because it's a fact to begin with. No, the professor is giving you a statement that the professor said is true, which is not the same thing as the professor gave you a fact. Okay? I'm not saying that you should not trust your professor, but you should always have your own method of double checking things. Is that okay? All right? All righty. So now we move on to the next stage, which is to get rid of that plus. Okay, so let me remind you what plus we are talking about. T of I plus 1 is B of xi yi plus B of qi ti. Okay, it has the same structure as the one in addition, but the reasoning is, I mean, the structure of the proof is going to be about the same, but it is the steps are slightly different. So now we're going to go through the whole process and say, okay, what if you are told that b of xi yi is a 1 to begin with? What does that imply? Can I figure out the exact values of xi yi knowing that b of xi yi is a 1? The answer is yes, because in the truth table, only one row has a 1. So that means if the expression of b of xi yi is a 1, I know exactly what xi has to be, and I know what yi has to be. So in this case, xi has to be a 0, and yi has to be a 1. Okay, so what does that imply? Well, that implies q of I, which is the r of xi yi, is going to be a 1. Yes, the little caret thing. You mean this thing here? That's conjunction, which is and. It's the mathematical conjunction and. So in C++, it would have been a ampersand ampersand. Yep. All right. Okay, big deal. If Q of I is a 1, so what is the big deal? So if Q of I is a 1, it is the same thing as saying U is a 1 in the previous truth table. Okay? And if you look up that truth table, I intentionally am not switching back to the previous slide because I want you guys to look at your own notes. So with the previous truth table for the B function, what happens for all the rows where U is a 1? What is the value of the B function? Both of them are zeros. Oh, look at that. So now we can verify that B of Qi Ti is guaranteed a 0. That's why the truth table is useful, because you can see patterns from the truth table itself. So when you look at the whole thing, this means if you just tell me that B of Xi Yi is a 1, I can come to a conclusion that Q of Qi B of Qi Ti has to be a 0. Does that remind you of the first step of proving that you can use or instead of plus in the case of K of I plus 1? The reasoning is a little bit different, but the structure is the same. So now we have to go the opposite way, which is to say, okay, what if I tell you that B of Qi Ti is known to be a 1, okay? But I'm not telling you anything else. I'm just telling you that B of Qi Ti is a 1. What can you tell me about the individual components? Same thing, right? It's like, okay, just using the same method here, we know that Qi has to be a 0 and Ti has to be a 1. Okay, all right, that's cool. But Qi being 0, eh, we have two cases, okay, for Qi to be a 0 because Qi is the R, oops, hmm, Qi is the R of Xi, Yi, and there are two rows where R of UV is a 1. So in one case, U is 0 and V is 1. In the other case, U is 1 and V is 0. Okay, but I can just go like, okay, but there's an easy way to, well, okay, I'm not going to use the easy way. Let's spell out the long way. There are two conclusions. One or the other has to be true. The first one is Xi is a 0 and Yi is a 1. And then the other one, this is an or, Xi is a 1 and Yi is a 0. So what is the big deal? Okay, I'm missing, nope, I take it back. I made a mistake. Darn it, I made a mistake here because we know this is a 0. This only is working if Qi is a 1. So my mistake, I apologize. Let me fix this. Okay, yep, actually that. They both have to be the same. Either they are both 1s or they're both 0s. Because Q of I is known to be a 0, and the only time Q of I or R of Xi, Yi is a 0 is when Xi, Yi are either both 0s or both 1s. If they're both 0s, then B of Xi, Yi is a what? What is the borrow when you subtract 0 from 0? Yep. And what is the borrow when you subtract 1 from 1? Also a 0. So now we are done because both of these come to the same conclusion. So that means if you tell me without explaining about anything else, that B of QITI is a 1, I can make the conclusion that B of XIYI has to be a 0. So now we're in the same situation that only one of these two, up to one of these two can be a 1. They cannot both be 1s. So using the same argument that we also used on Tuesday, we can now go like, oh, okay, so that means I can rewrite this whole thing with an OR because both the two sides cannot be 1s at the same time. We can at the most have one of them being a 1. So that means the plus or addition versus disjunction or is going to work out exactly the same way in all cases. All right. So are we doing okay so far with the derivation? So I can probably rank your reaction, okay, in terms of you know where you're standing in this class. If you are feeling this is really boring because it is really the same kind of stuff that we talked about for addition, except with a little bit of a twist, then you are definitely keeping up with all the material. If you recognize that this has resemblance to the addition that we talked about on Tuesday, but the details is still a little bit foggy, but you're getting the general idea, you're doing okay. Okay, you're probably at the peak of the normal curve. On the other hand, for people who are feeling, I really don't know how this class has anything to do with the class on Tuesday, I would start to worry. But it's still early in the semester, so for people who are not making the connections, there's still time to catch up. Okay, the key is it has to start now. Okay, because before we stack even more stuff on top of what we have already talked about, it's important to catch up at this point so that people do not fall further behind. Okay, so I just wanted to mention all of these things, not to discourage people. That was not the intention. The intention is for people to kind of do a self-assessment of where they stand in the class and what they can do at this point of the semester to, if anything, to catch up with the rest of the class so that they would be successful by the end of this class. All right. So you can email me or message me in Canvas if you think I'm spending too much time being in dad mode. You go like, dad, stop doing that, Tech. Don't be my dad. I don't want you to be my dad. Okay, you can send me an email and I will refrain from making these recommendations because otherwise, I would treat you more or less. It's not intentional, but I would treat you like my children. Okay, I can see different reactions from different people in this class. Some people are going like, no, you cannot be my father. In case you haven't noticed, I'm a big fan of not only Star Wars, but Darth Vader. So, and guess what? My son is actually Luke. And my daughter is, yep. All right. Shall we proceed? All right. So the way we're going to proceed at this point is to go like, okay, this is all great. Okay, equations and mathematical stuff and whatnot. What does this have to do with computer architecture and organization? Well, we're going to build a circuit. Okay, we are going to build a circuit to perform addition and subtraction. Okay, given what we already know, we now have everything that we need to build a circuit. All right, so I think we got plenty of time to do it, so let's do it. All right, so to do that, it is better for me to use Logisim because at the end of the day, I can give you the file and you guys can play with it. All right, so let's see. Put this here. There we go. All right, let's build the entire circuit. But I'm gonna shortcut a little bit here. Instead of building everything out of transistors, I'm just gonna use the gates over here for and or not. Okay, is that okay? Or do you guys really want me to go all the way down to transistors? Hmm? Okay, so we'll use the pre-made gates. Okay, because I think there's a certain advantage of using the pre-made gates because that will also help to introduce the symbols for the gates. So I think that is actually helpful too. All right. So the first thing we're going to do is to make a, so I'm using add circuit to create what we call a half adder. Okay, that's actually the name of the circuit. You can actually look it up. It is actually called the half adder. What does that imply? If I name a particular circuit a half adder, what do you think it implies that, oh, okay, if we have this, we're going to have that too? A full adder, right? Okay, so this is the kind of pattern recognition that I'm talking about. It is recognizing a pattern and go like, oh, okay, if there's a half, that's probably a full or whole. Okay, it turns out it's called a full adder, but this is called a half adder because it is about one half of a full adder. So what we want to do with a half adder is to implement the R function and also the C function at the same time. So this is going to be computing the R of UV and also the other one, which is C of UV. With a normal C function, you cannot return two values at the same time, but in a circuit, we can certainly have two output pins, one corresponding to each one. So I'm just going to create the circuit input pins first. So we got two input pins and then we got two output pins. And I'll label these so that you can start to think about, how do we do this? This is oh no, this is U. This is input U, which is corresponding to parameter U when I describe the functions. This is parameter V. This output pin is going to represent C of UV. And then this output pin is going to represent the other output, which is R of UV. And that's what a half adder really is. A half adder is a circuit that takes two inputs, U and V in this case, and it has two output pins. One is computing C of UV, and then the other one is to compute R of UV. Okay, so now the question is, what do we do in between? Well, you just have to remember how do we compute the C function. The C function is a conjunction, so we can just go to these gates here, pick up an AND gate, make it look nicer. Okay, so we only need two inputs in this case. And then I will stash it here. Okay, and the inputs will be coming from U for one, and then coming from V for the other one. Okay, so there we go. All right, so that's one part of a half adder. The other part of the half adder has to compute R, and I already mentioned on Tuesday that it is also known as exclusive OR. So we just pick out an exclusive OR gate, change the number of inputs to 2, make it look a little bit smaller. It doesn't have to be as huge as it was, and then just make the connections pretty much the same way. Okay, put this over here, and then you'll put this over here like so. And now we have a half adder. Okay, so let me repeat what I said a little bit earlier. A half adder is simply a circuit that will compute the C function and the R function. It has two output pins, one pin for each one of the function that we're computing. Okay, so do we have any questions about the half adder circuit? Okay, so now now it is useful to actually document the pins because otherwise I cannot remember which one is which one. So I'm going to say U, B, C, and R. Okay, because if I don't label things, I'm going to start to forget things. So I'm just going to do this and move this one over here, and C is here, and R is over here. Cool. All right. So that's my half adder circuit. So now I can now create the full adder. So now I go to add circuit. This one is called the full adder. So a full adder, as the name implies, probably contains how many of the half adders? How many halves makes a full? Two. That's right. So I'm going to slap two of these things here. All right. And I'm going to have to state here what a full adder is going to do. So in text mode, I'm going to mention this is what a full adder is going to do. The full adder will compute S of I. So S of I is the R of Qi Ki. It will compute K of I plus 1. Okay, so I'm going to put it like this. K of I plus 1 is C of Xi Yi or C of Qi Ki. And those are the outputs. And then the inputs would be Xi, Yi, and Ki. All right. So now we use input pins to denote the input to this whole thing. So we have Xi as an input. We have Yi as an input. And we are also going to have Ki as an input. Those are my inputs. Ki, there we go. And then for the outputs, we have Si as an output. And then for the other output is going to be K of I plus 1. So that's my other output pin, which is really just K of I plus 1. So when I use K of I plus 1, I put brackets around it just so that it's easier to understand that the index is I plus 1. It is not K of I itself plus 1. So there we go. All right. So how do we do this? We know the input, we know the output, we also know the relationships between the input and the output. So now the question is, with two full adders already implemented and slapped onto this circuit, how am I going to do all this stuff here? I think the first question for most people is to say, but what about Q of I? Q of I is not one of the input pins. Where are we going to get Q of I? How do we compute Q of I? What is the formula for Q of I? Q of I equals to R of Q of I is R of Xi Yi. Okay. Okay. I have things that I want to say, but I'm going to refrain from extensive dad mode in this class. Okay. So we have, oh, wait, look, we have R here. So that means, and we have Xi Yi here. So that means, oh, okay, look at this. If I just feed this Xi to one of the input, which is um, the U over here, and I take the Y to the other input, this output here is my Qi. I'm going to pause here to make sure that we all understand why I said where the mouse pointer is pointing to. That's Qi. Qi doesn't need to be an input because we can compute Qi from Xi Yi. Oh, oh, cool. That is cool. And then now we go like, okay, what about the other stuff that we need R for? So R is S of I is R of Qi Ki. Oh, okay. So we can now do this. Um, Use one of the input for Ki. Okay, I'm going to use the second one for Qi. Ki, sorry. So that is one part of computing Si. This is my Qi. So that means I just need to take this Qi and just route it all the way back here and make it to the other input of the other half adder. So that means This R here is what? What is this R? It's ready to go to one of the output pins. Which one should it go to? S of I. Very good. Because this particular R output is the R of QI, KI, which is our SI. Oh, okay. Well, that's kind of cool. And now we have something else. Okay, so now what is this? If I have to describe this particular output pin, it would be the C of what? XIYI. Very good. So this is X of C of XIYI. And why do we need C of XIYI? Oh, it's a part that we need in order to compute K of I plus 1, which is this particular output pin. This one here is the C of QIKI. But those two need to be ORed together. So that means, okay, we need an extra OR gate to do just that. So now we go narrow, go to just 2, like that. And now we slap it here. Okay. And then we just take this one and go like, you go to one of the inputs. And then this one goes to the other input. Now we have K of I plus 1. We're done. Are we doing okay so far with this? Yes. How do I how do I put the half adders into the full adder? Um, because I created the half adder, it becomes a component that I can choose from. In other words, if I compact this, okay, get rid of this, you can see the half adder that I have created becomes one of the components that I can use. So that's why I have to create the half adder first, because otherwise I cannot use it as a component. Absolutely. All right. So yes, go ahead. Mm. You instead of using the medium, I think you have to choose the narrow. It's one of the properties of a gate. It controls the visual size of the thing. Okay, so let me go back here. You found it? Okay, so it is the gate size that you have to change. I mean, it's not really functional. It's just that it looks nicer when it's not gigantic. Yep. Yeah. Well, I'm gonna give you guys this file too, but yeah. All right. So are we doing okay so far? All right. So now I have all the components that I need to make a what I call a 3 by 3 adder, which means the input has 3 binary digits. Each one of the input has 3 binary digits. The output, which is the sum, also has 3 binary digits. And then we have K3 on its own because it's just kind of hanging out there. It is not part of the sum. So now we create the overall circuit. Okay, so I can use main for that purpose. All right, so it is always useful to think in terms of input pins and output pins. So I have two of these things. So these are 3-bit input pins, which means even though it is seen as one input pin, it has 3 bits in it. So now we have this is Y, this is X, and I'm going to do something that you guys will go like, but what is that? Well, I thought we have an assumption. This is K0. In other words, we are no longer saying, oh, K0 is always a 0. We make it an input pin. Okay, so those are all the inputs. And then the output is going to be the sum. Okay, so this is the sum, and the sum has the same width as X and Y. So that's why it's a 3-bit thing. And then we have one individual output pin that is representing, in this case, K3. So now we just have to go like, okay, so what do we need in between to get the sum computed and get K3 computed? I think most of you are thinking full adders. It would make sense, right? Because otherwise, why would I be constructing full adders? So the question is, how many of those do we need? What do you think? Three. We need three of those because we need one per column in the addition. In other words, one of these things here, one full adder, is doing the calculation of one column. Because remember what a column looks like. You know the x, you know the y, you know the k of I, right? And you want to compute as a result the s of I and the k of I plus 1. That's exactly what a full adder does. It handles one column of the multi-digit addition. Is that okay? All right. So that means in 3-bit by 3-bit addition, we're gonna need three of those. Okay, so here's one, here's another one, and here's another one. Okay, and I forgot to label the pins, so let me go back and label those. And the way to do it is to say X, Y, K, S, I. Okay, so now I can just label these X, Y, K, and then on the outside output it has sum and K of I plus 1. I'm gonna have to give it better names. There we go. This is KI. Oh, hmm. Okay, that doesn't work out the way that I thought it would. Get rid of that. I have to select the text first before I make changes to it. Nope, doesn't want me to change that. I guess it is fine. Okay, X, Y. This is KI as an input, and oh, I cannot remember, whether the top is the sum or the bottom is the sum. So the one trick you can do is to just go to the pin and click on it. You can see there's a picture in picture. This is my carry. This is K of I plus 1. And then if I click on the top one, oh, the pin. Come on, let me click on the pin. Ah, it won't let me do it. Okay. But that's the trick to find out which pin is which pin. This is sum, and the bottom one is the one that is K of I plus 1. There we go. Okay, now that we have labels, I think it is easier to make the connections because otherwise I cannot remember which one is which one. This is a 1-bit thing. This is a 3-bit thing. So what do I need? Splitter. That's right. Okay, so we need a few splitters. Okay, in fact, we need exactly 3 splitters, 2 for the input, 1 for the output. So it's going to be a 3-bit splitter because this side here, the merged end has 3 bits. That determines the width of the splitter, which is also 3. But we also need a fan out of 3 because every single bit has to go to a specific place. So we have 2 of these. Okay, so we got one for x, one for y, and we also need one for the sum. Except in the case of the sum, it's going to be pointing in the opposite direction. So it's going to point west, and because the merged end is going to go to the output pin, like so. All right, so now we are ready to make some connections. Okay, like that. This is x0. So x0 can go to the first, this pin over here. X1 is going to go to the x of the second full adder, and then x2 can go to the bottom one, which is here. And I have no idea why it turned blue. I think I accidentally turned off simulation. Nope, it's still on. I have no idea what just happened. All right. So this is Y0. This is Y1. Like that. And this is Y2. It goes here. And then on the output side, the sum are the easy ones to deal with. This is S0. So it just goes to the bit 0 of this particular splitter. This is S1. So S1 kind of goes here. And this is S2, which goes here. And this is the actual sum. Make that connection here. All right. Now, the reason why this is red is because I have not made the connections to the case. So now the question is, how am I going to deal with the case? Well, we can start with K0. Where do you think K0 should go? Sorry? The top one, right? The K on the left-hand side of the top one. Yep. Because that's also where X0, Y0 went. So might as well, also route K over there. And the diagram is looking kind of ugly at this point, and it's going to get uglier. So if this is K0, what is this? That's K1. And where do you think K1 needs to go? This K over here. So I can make it happen. There are several ways to route the signal. Neither is really clean, okay, because I didn't really put the pins to good convenient places, but it works okay. This is K of, nope, it's K of 2. Because K of 1 is here, we use K of 1 to compute K of 2. So K of 2 is going to go to the K of 2 that serves as an input, which is over here. So if this is K of 2, this has to be K of 3. So K of 3 is just an output, like so. So now we have a 3-bit by 3-bit adder. It's time to test it. So how do we test this particular circuit? Well, right now it is already testing. Okay, it's basically saying 0 plus 0 with no with K0 being 0 has a sum of 0, also with no overall carry. Yep. Because this way we can daisy chain 3-bit by 3-bit adder to have 6-bit, 9-bit, 12-bit adders. Hmm? Nope, it's not, because once the first one is always 0, but when you daisy chain, then it's not always 0. Okay, let me answer the question first before we come back and test the circuit. So the thing is, um, if you want to make a 60-bit adder, do you guys feel you're up to the task to kind of do this? Except you have 60 bits for the input pins, 60 of the full adders, and 60 things going to the merger to become the sum that is 60-bit wide. Who wants to do that? Not me. Okay, so it's good to be scalable. Okay, in other words, it's good if 60 is not really a good number because it's not a power of 2, but if it's a power of 2, that means I can have one full adder, and then we can have a 2-bit adder. Then by combining two-bit adder, I have a 4-bit adder. By combining two 4-bit adders, I can have an 8-bit adder. By combining two 8-bit adder, I have a 16-bit adder, and so on. So that's the reason why we want to be able to daisy chain things, because now we can make bigger things by just scaling, by copy and paste, but only once. And every time you do that, you're doubling the size of the adder. Is that okay? So now, if I just kind of go like change the name of this circuit, because it probably should be changed to something like 3 by 3, okay, 3 by 3 as an adder. So if I want to make a 6 by 6, how do I do it? To the project, add the circuit, call it a 6 by 6 adder. So now I have a 6-bit input pin and a 6-bit input pin again, a 6-bit output pin. Oops, not that, but here. Make it 6-bit. And then we still have the single bit stuff, okay, because this in return can also serve as a component for a larger adder. So this time, instead of using the full adder, I can now say, oh, okay, we just need two of these things. So the first one takes care of the first 3 bits. The second one would take care of the other 3 bits. Once again, we need a splitter, but the splitting is a little bit different this time. So each splitter needs to be 6-bit wide because they will connect to the 6-bit input pin, the 6-bit input pin, and also the 6-bit output pin. So I'm going to need 3 of these. Okay, so one more like so. This one goes here, and then this one goes here. So one is for X and one is for Y, and then this last one is for the sum. And we need to change. Nope. Uh, I need to change the facing. There we go. West, like so. Stick it up here. There we go. Okay. So now I can now make a really easy connection. Bit 0 to 2 goes here. Bits 3 to 5 goes here. This is Y. So now we have these going to here. These would go here. And then this will, let's see, yeah. So this will be the first 3 bits or the least significant 3 bits of the output. And I think I made a poo-poo here. I think it's this one. So that goes here. That goes here. And now we have a little bit of a problem because it's like, where do we get this K0, so-called K0? But that's not K0 because the second 3 by 3 bit adder is handling bits 3 to 5. So this is technically our K3. So where am I going to get my K3? My actual K3 is the output from the top 3 by 3 adder. So that means I need to take this. Come on. Okay. Two-hand operation. Like so. This is the actual K0 from this circuit's perspective, and there's no really clean and easy way to route it. Well, I mean, I can thread it through like that. I used to do board layout, so this doesn't really bother me much. And then this is the actual output to go here. This is why we have K0 as an input pin, because it allows me to daisy chain two 3 by 3 bit adder by connecting the K3 output of the first 3 by 3 bit adder to become the so-called K0 of the second 3 by 3 bit adder. So now that we have a 6 by 6 adder, I can easily make a 12 by 12, and then 24 by 24, 48 by 48, and so on. Yep, yep, yep. Because we know each one of those, I didn't quite label it, but we know each one of those ICs or integrated circuit is by itself a 3 by 3 bit adder. So that means the XY inputs are 3-bit wide. The sum output is also 3-bit wide. And this is the reason why K0 is always an input pin, because I want to have the option to daisy chain things. So we are almost running out of time. There is a lab today. We're going back to the same lab that we should have done on Tuesday. But to test the circuit, so let's go back and test the circuit a little bit. So if I were to add 5 and 4, okay, so I want to add 5 to 4 in base 10. So 5 is 101, 4 is 100. So now I look at the output. It's like 5 plus 4 is a 1. Well, sort of. 5 plus 4 is a 1. with a overall carry. But that overall carry is a digit 3. So what is digit 3 representing? If I say I have 1 for a digit 3, what quantity is it representing? In base 2, this is all base 2. 8, that is correct, okay? Because we are looking at 2 to the power of 3 because that's the position. So that means the actual result of the addition is 1, which is the sum bit, plus 1 times 8 in this case. 1 plus 8 is in fact 9. So 9 is 5 plus 4, okay? It works out, all right? So I think this is the end of today's lecture, is to give you an idea of how we can turn all that math stuff, okay, the notations, the expressions and whatnot, into actual circuits, and have the circuit organized in a way that we can easily expand it to become wider and wider. Now, there's one disclaimer I need to make before turning on the lab so that you guys can actually do the lab. The disclaimer is easy, okay? And you guys would go like, "Oh, you just wasted the whole class doing this." No one would actually implement an adder the way that I just described it, okay? You go like, "Man, you just wasted my time." Okay, the first thing I would think is on your mind is why, okay? It seems like this gets the job done. It is consistent with the theory that we have been talking about. Why would anyone not use this particular method? Yes. So it's called carry ripple. So the technical name of this particular adder is called a carry ripple adder, which means the carry bit has to ripple through linearly throughout all the bits, which also means the amount of time for a 64-bit adder to do the job is twice the amount of time of a 32-bit adder. The amount of time of a 32-bit adder to perform the operation would be twice the amount of time of a 16-bit adder, and so on. It is big O of n. The more bits you have to add, the longer it's going to take because the carry bit has to propagate through the entire circuit for everything to be correct. So if this method is slow, it implies there's a faster way to do it, right? For years, I talk about a faster way, which is called a carry look ahead adder. But the math involved in a carry look ahead adder is a little bit complex, okay? And I ended up having to spend like 2 classes to talk about that particular mechanism. And then I ran out of time at the end of the semester to talk about other things that I really also should spend time on. So right now, I'm not going to talk about carry look ahead adder because it just takes too much time. But it is important to point out that this one, even though it looks like it works, it does work. But no one is going to do this in silicon because it is not efficient. So for now, we just have to say that, okay, it works. It's great as a classroom teaching, example, but this is not what people actually do when it comes to processors. Is that okay? It's simply a matter of time. I just do not have enough time to go over the carry look ahead mechanism. All right, with that said, I will give you the lab for today. So depending on how much you remember from, let me see, the base conversion stuff, it might take you like 15 minutes to get through everything today. It might take you a little bit longer. It really depends on how much of the base conversion material you are retaining. You can use the TA, the GPT TA to help you in this case. I've never tried it before, but I think that would make it like super easy. All right, so this is the one for base conversion, and the access code is what you need to get into it. It is heptapod. There you go. So if you want to take a short break, you can do so. It is due at 11:50 today. Um, Once again, it depends on how much you remember from base conversion. Wait, no, that is not true because I actually talked about base conversion just today. So it is based on base conversion, and you can use the GPT teaching assistant to help you out. It should not take too long. That's my guess. All right, so I'm done with the lecture. I will go back to my room, get some